Stereochemistry is the three-dimensional aspects of molecules. Normally when we draw molecules, we draw them on a flat surface. But we have to keep in mind that molecules are actually three-dimensional and there are consequences to this. For some molecules, they're actually identical to their mirror image. Some are not. And there are consequences to that we're going to talk about as well. One object that we're all familiar with that's not identical to its mirror image are your hands. So if you look at your hands, they are effectively mirror images of each other. So if you hold them like this and imagine a mirror in between them, one would be reflecting the other. But if you try to line them up with each other, you can't do it. They're not what we'd say, they're not superimposable with one another. Or another way to say this is the mirror images are actually not identical. This property of any object where it's not superimposable with its mirror image is known as chirality. So a chiral object is not identical to its mirror image. An object that is identical to its mirror image would be called achiral. So the A just means the opposite of chiral. So if we look at the two objects on this slide, we have just a regular chair first. The mirror image of that chair is actually identical. If you imagine taking so here's our original chair, here is the chair reflected through a mirror. If you take the reflection, turn it, and line it up with the original object, they're completely identical. That is an achiral object. Now if we compare that to this desk, which is a chair plus this side table, that's actually a chiral object, because now we have the mirror image is not the same as the original object. If you imagine swinging the mirror image around and lining it up with the chair, the desks will be on different sides. And one thing that you can kind of look at when you're trying to determine whether an object is chiral or not, any object that has a plane of symmetry in it is not going to be chiral. So if you look at the original chair we were talking about, if you cut that in half, the right side is the mirror image of the left side. And so you have a plane of symmetry in that object, and it is not chiral. Whereas the desk here, if you were to cut that object in half, the right side is different than the left side. Putting the little table on there breaks up the symmetry of the chair so that it's now asymmetric, and it is a chiral object. Another example that most of us are familiar with are faces, and this just happens to be mine here, that most people's faces are not symmetric. So if you look at my face here, and I basically took this in Photoshop and cut it in half and have the right side and the left side, and then on the bottom here, took the right side and took the mirror image of it and joined it back together, and then did the same thing with the left side and joined it back together. The two images at the bottom are actually symmetrical versions of my face, but neither of them actually look like mine, which is asymmetric. So both of the faces at the bottom have a plane of symmetry, whereas the original doesn't. Well, what's that have to do with molecules? Well, molecules, just like any other object, can have chirality. So if we look at the molecules on the top of that slide, and I brought the models here, that if you hold these in this type of orientation right here, they are mirror images of each other. And if you try to superimpose one on the other, you notice that all of the atoms line up perfectly with one another. These are not chiral molecules. So the mirror image of this molecule is identical to itself, and so it is not chiral. Whereas when we have a molecule like this, where we have a tetrahedral center and we have 4 different groups attached to that tetrahedral center, it's actually chiral. It turns out there's actually 2 different ways in which we can arrange the 4 different groups. And so each color here represents a different group. And the way I'm holding these right here, you can see that they are mirror images of each other. It's basically the same models that are in that picture. But when you try to align or superimpose all of the atoms in here, you can't do it. So here we've lined up the purple and the red group, but the blue and the yellow ones are reversed. And if I were to turn this where I lined up the blue and the yellow, then the red and the purple would be reversed. And so these are non-superimposable mirror images of each other, and they are chiral. Now getting back to the situation where we have 4 different groups attached at a tetrahedral center, that's known as an asymmetric center. And anytime we have an asymmetric center, there are 2 possible ways of arranging those 4 different groups. And we need to have some way of distinguishing which actual configuration we have around that asymmetric center. And so the system that we use is shown on this slide, where what we need to first do is to assign priorities of the groups attached at that asymmetric center. And so the molecule in this slide here is you have a bromine, we have a chlorine, we have a fluorine, and a hydrogen all attached at that asymmetric center. We need to assign priorities to those groups according to the Kohn-Ingold-Prelog rules, which basically states that as you move away from the asymmetric center, if you come to an atom, if you come to a difference, the atom with the higher atomic mass is the one with the priority. And so bromine is going to have the highest priority, then chlorine, then fluorine, then hydrogen. If you had identical atoms, you would move another bond out and compare those. And if those were identical, you'd move another bond out. And you'd keep doing that until there was a difference. So when you do that, then what you need to do is to orient the molecule such that the lowest priority group is directly behind the asymmetric center. So the 4th priority group here would be behind, kind of in this drawing that we've shown here, where the other 3 groups, 1, 2, and 3, are kind of projected out toward you. When you do that, the 3 groups are either going to go in order, 1, 2, 3, either clockwise or counterclockwise. If they go around clockwise, that is what we call the R configuration. If they go around counterclockwise, that's what we call the S configuration. So if we look at the molecules then on the bottom part of this slide, we have different isomers of 1,2-dibromocyclopentane. And they only differ by the relative orientation of the bromines in 3-dimensional space. They are what we'd call stereoisomers of each other. They're connected in the same way, but they are pointed in different directions. So this would be the RR stereoisomer, because this asymmetric center here, if you look at the bromine, would have the highest priority, the carbon attached to the second bromine next, and then the CH2. And the hydrogen that's not shown explicitly in there goes into the page, right? And so the 3 groups go around in a clockwise direction. That is the R. If you do the same thing with the other asymmetric center, it's also R. If you look at the stereoisomer here, both of those are S. And the one at the bottom of the page, we have the RS configuration. The RR stereoisomer and the SS stereoisomer are mirror images of each other, what we would call enantiomers. And then we have the definition of that on the next slide. Whenever you have a molecule with asymmetric centers and you convert all of the R configurations to the S or all of the S to the R, you end up with the enantiomer. The molecule at the bottom of this slide is a different stereoisomer. It's what we would call a diastereomer of the other 2, where you have at least one difference in configuration at one of the asymmetric centers, but not at all of them. And so if we look at our definitions on this slide, enantiomers are mirror image stereoisomers. Diastereomers are stereoisomers that are not mirror images. And so the question is then, well, what does this matter? What do we really need to understand about this? Well, if you have a pair of enantiomers, the mirror image isomers, they behave identically in most situations. If you look at the physical properties of them, things like melting point, boiling point, index of refraction, whatever you want to look at. If you look at spectroscopy, you look at their IR spectrum, their NMR spectrum, they are identical. If you have diastereomers, they behave differently. So on this slide, we have at the bottom an example of three different diastereomers of menthol. And I just put the melting point as one of the physical properties, and you notice the melting point is different for all three of those. If you look at the top, we have enantiomers of limonene and carvone. If you compare the boiling points of the enantiomers of limonene, they're identical. In fact, any other physical property you wanted to measure, they'd be the same. And same thing with carvone, that the boiling points of these two are the same. Interestingly, though, if you were to smell these chemicals, they smell different. So the R-limonene smells like oranges, and the S-limonene smells like lemons. And for carvone, the R enantiomer smells like mint, and the S enantiomer smells like caraway. And so the question then is, well, why do they smell differently if they behave the same otherwise? Well, it turns out that in nature, you have basically single enantiomer molecules. That the basic building blocks, things like the amino acids or the sugars or nucleic acids, these all occur in nature as a single mirror image form. And so when you have single enantiomer molecules, your biomolecules interacting with both either mirror image of another molecule, those interactions are actually different. It's something we refer to as chiral recognition, which is basically the ability of one chiral molecule to just recognize which enantiomer of another molecule it's interacting with. And kind of the best analogy to understand this is the handshake analogy. Like if you went to shake somebody's hand and you put out your right or left hand, as long as they put out the same hand, you can effectively shake their hand, right? So here's an image like two right hands locked together perfectly in a normal handshake. But if you put out your right hand and the other person puts out their left hand, they don't fit together correctly. That one person's hand, which is only one mirror image form, is able to differentiate between the two mirror image forms of the other person's hands. And molecules behave in a similar way. That if you have two mirror image forms of some molecule interacting with biomolecules, which only occur as a single enantiomer, those biomolecules can tell the difference between the two mirror image forms of the other molecule. And so this is really important, let's say, for example, in the pharmaceutical industry. You want to make a drug, and one mirror image form of this drug does what it's supposed to do. The other one is not going to do the same thing. You know, in the best case scenario, it would do nothing, but in the worst case scenario, it would cause severe damage. And so we need to have ways of separating enantiomers, or we need to be able to make them just as a single enantiomer to start with. So generally when we synthesize molecules, starting from simpler, readily available starting materials that are not chiral, and we do whatever chemical reactions to build up a larger, more complex molecule that is chiral, we're going to be making an equal amount of both mirror image forms. There's really no way to make one enantiomer and not the other without having other chiral molecules intervening in that process. So if all of your starting materials, all of your reagents or catalysts are not chiral, there's no way to get one enantiomer in preference to the other. And so it's very common when you go into the lab and make some molecule that you're going to have what's known as a racemic mixture, or the racemate. So at the top of this slide, we have some compound A that we have equal amounts of both enantiomers, which we'd call, again, the racemic mixture or the racemate. If we want to be able to separate those enantiomers, the only way we can do this is by converting them into diastereomers. And so we need to have some chiral reagent. So let's call that B. And let's say we have a single enantiomer of that. And so, well, where do we get a single enantiomer of that? And typically we get it from nature at some point, right? So what would we call the chiral pool, the pool of biomolecules that we can extract and isolate. And what we also need in this case for this scheme is some way to bring those two together. A and B have to be linked together, either one in three ways, covalently linked together, or acid-base chemistry, we can make salts, or other types of non-covalent intermolecular interactions to hold these together. But once these two are together, we now have diastereomers, right? Because we have both enantiomers of A, we only have a single enantiomer of B, and if you imagine both of those just have one asymmetric center, now we have RR for one and SR for the other, effectively, which are diastereomers. Diastereomers are always different. They always have different physical properties. We could find a way to separate those, and then we can just undo what we did in the first step. So if we're making covalent bonds in that first step, which is known as chiral derivatizing reagents, we have to have some reaction specific for a functional group in that molecule, do the derivatization, do the separation, and then do the opposite of that first reaction. And so it's very inefficient and very, there's losses in each of the chemical reaction steps. There's a lot of waste in the separation process and so forth. Salt formation is a little more straightforward. The example down at the bottom of this slide shows a salt formation where here you have both enantiomers of lactic acid. You react with just a single enantiomer of phenylethylamine. And again, this is a molecule that's derived from nature. You can form these two different salts, which are diastereomers of one another, and you can then find some solvent that will fractionally crystallize one in preference to the other. And so you can separate them. And then simply to get them back, if you want to get the acid back, just add a stronger acid, like dump in some HCl and then extract your single enantiomer product. The non-covalent interactions are typically what's used when you do chiral chromatography. So if you have a single enantiomer of some chiral selector attached to the surface of silica, and this is all packed in a column, when you pass a solution of your racemic mixture through there, one enantiomer can bind more tightly to the surface than the other. And so as it moves down the column, one will move through the column faster than the other, and they'll separate. And so you can have a container at the bottom of the column collecting one enantiomer than the other. But all of these require extra work and involve generating a significant amount of waste. It would be nice to just be able to go directly to a single enantiomer, which you can with what's known as asymmetric synthesis. Generally, again, any chemical reaction that starts with achiral molecules, where all of the reagents are achiral also, is absolutely going to produce both enantiomers in equal amounts. The only way to produce one enantiomer in preference to the other is by having the intervention of some other chiral molecules. And in this example here, we're looking at chiral catalysts. And in fact, the people that did this work won Nobel Prizes in 2001 for developing this chemistry. So it's still relatively recent, and it's extremely important. So Knowles, Noyori, and Sharpless shared that Nobel Prize in 2001. Knowles and Noyori worked on asymmetric hydrogenation reactions. An example is shown on this slide. So you take this alkene, and you can hydrogenate it, add hydrogen across the carbon-carbon double bond. That generates an asymmetric center. If you do that with an achiral catalyst, you get an equal amount of both enantiomers. But if you use this catalyst shown on this slide, where you have this phosphine ligand coordinated to the metal center, the phosphine ligand being chiral, now you can get one enantiomer in preference to the other. In fact, they get 95% EE in this particular reaction. The EE is how much more of one enantiomer than the other. So not quite, it doesn't quite give you just one enantiomer, but it gets pretty close. This reaction down below is the Sharpless dihydroxylation reaction, where this alkaloid that's shown on the slide can coordinate to osmium tetroxide, which makes it chiral, and it can deliver the oxygens to either one side or the other of your alkene to give you one enantiomer or the other in really high enantiomeric purity. A little more recently, another Nobel Prize was awarded to List and Macmillan for developing asymmetric organocatalysts. And so doing, again, conceptually the same thing where you're taking achiral starting materials and you're making chiral products, but you're making more of one enantiomer than the other. But instead of having metal catalysts, they're doing it with organic molecules that are the catalysts. And so you don't have to worry about heavy metals contaminating your product and things, and you can use basic your basic separation techniques that you use in organic chemistry. And so here's an example of an aldol reaction, a Diels-Alder reaction, and there's many more reactions that have been developed by these groups. And so just to summarize this unit here, chiral objects, including molecules, are anything that's not superimposable with this mirror image. Chirality in organic molecules is usually caused by one or more asymmetric centers. It turns out it's not the only way. We'll talk later about like other ways that you can have chirality without asymmetric centers, but most of the chiral molecules you'll encounter in organic chemistry have at least one, if not more, asymmetric centers. Sometimes, and I should also point out, sometimes these are referred to as chirality centers. So if you hear the term asymmetric center or chirality center, they can be used interchangeably. I just prefer the term asymmetric center. Mirror image molecules are known as enantiomers. Stereoisomers that are not mirror images of each other are known as diastereomers. Enantiomers have identical physical properties. So melting point, boiling point, other things like that. They also look the same in spectra, the IR spectrum, the NMR spectrum. They behave differently, though, when interacting with other chiral molecules. And this is the concept of chiral recognition. And single enantiomer molecules can be attained from effectively three different sources. Either from the chiral pool, which means we get it from nature, or we make a racemic mixture and we separate those enantiomers, or we start with achiral starting materials and we have chiral catalysts or chiral reagents and we make one enantiomer in preference to the other, or in other words, asymmetric synthesis.